Hello kids, ready for our last volume of revolution lesson. So before we have been doing potato chips and lifesavers. So I want to review that with this warm-up where I've given you this shape, area bounded by the y-axis, the line x equals 2, the line y equals 0, and the curve, which is a parabola, right? So the line x equals 2 is here. The line y equals 0, there. The curve x squared plus 1. And the y-axis. I'm going to rotate this around the y-axis. Right? Now, question. Is there space between my figure and the axis of rotation? No, right here. But yes, here. Space between the figure and my axis and rotation? No space. What the heck? Now before I go on, I also want to highlight, pun intended, some things about the axis of rotation is vertical, correct? My representative strip that I'm going to draw, since I'm rotating around the y-axis, is going to be sliced on the y-axis, right? Because I'm rotating around the y-axis, but I have slices that change boundaries. But notice that my slice, both slices, are perpendicular, right? This slice is perpendicular to the axis of revolution, right? Perpendicular to the axis of rotation. I'm sorry, revolution. The axis of revolution is vertical. My strips are horizontal. So, I am going to use the washer or lifesaver method, but I'm going to split it into two parts for the whole non-space, which really isn't going to be lifesaver at all. What is that going to be? That's right, potato chips. So, I draw my representative strip above that horizontal line, and I notice that the right part of the strip and the left part of the strip. I had the function y is equal to x squared plus 1, so I'm in the process then of getting x by itself. I don't need the plus minus here because I am just in the first quadrant. And then I set up, notice all my y values. Since I'm slicing onto the y-axis, I've got dy, which means the functions I have are in terms of y, and my limits of integration are y values. Now what's my integrand? Right? This is capital R squared minus little r squared. Capital R is a constant of 2. Do you see that? Right? The large radius right comes from Right, the large radius is measured from the axis of revolution to the right function. Well, what is this function? It's not a function at all, is it? It is a vertical line. How long is that radius? That radius is constantly 2. It doesn't change, right? If I click and drag from 1 to 5, that outside radius is constantly 2. But the inside radius changes, correct? When I'm doing the small circle, right, that radius goes to the curve, right? And I'll draw another one up here. Inside circle, the radius that goes to the curve. Outside circle. Radius goes out to the vertical line. Yeah? What the heck is this? Right? Well, what happens if you rotate a rectangle? What happens if you rotate a rectangle? You don't get a cone, you get a what? Cylinder. And what is the volume of a cylinder? Pi r squared times the height. Right? So pi, radius 2, constantly 2, so it's a cylinder, times the height. Good? So of course I can do this. None of this was very difficult integration. And I get 12 pi when I'm done. Okay? But note that that did take recognizing that I had lifesavers, right? All this part here was the lifesavers, which was all this part from 1 to 5. Right? And then this part, which you had to recognize was the cylinder. And of course you could have done that with potato chips, right? If you didn't recognize it was a cylinder, you would have done pi integrate pi integral r2 squared dy from 0 to 1, and you would have gotten, shocker, 4 pi. So is there another way to do this problem? Doesn't require such manipulations? The answer to that question is yes. There is another way to do this problem. Now, I'm not going to change my axis of rotation. My axis of rotation is still vertical. Rotation or revolution, whatever. And whenever we do potato chips and lifesavers, if your axis of revolution is vertical, then your slice has to be perpendicular to that, horizontal. Conversely, for lifesavers or potato chips, if your axis of revolution is horizontal, your slices have to be what? Vertical, and slice down onto it. So notice here, axis of revolution, vertical, my little representative slice is also vertical. That is not the disc or washer method. So, if I take the vertical slice and revolve it around the y-axis, look at what shape that is. Do you recognize it? It's a cylinder. It's a really thin, empty. This is empty, right? There's no space in here. It's a very, very thin cylinder. And that cylinder is parallel to the axis of rotation or revolution. If you make an infinite number of cylinders, an infinite number of cylinders, right? Here's just a cross section of a whole bunch of cylinders. You can find the volume of the solid of revolution by summing all of the volumes of those nestled, right? Nestled, that means one inside of another, all these shells inside one another. Kind of like, if any of you have ever seen the Russian Matryoshka dolls, right? Where you open a doll and there's a smaller, identical, except smaller doll inside it, open that one up and there's a smaller one inside of it. That's kind of what this is like. So the volume of a thin, hollow cylinder is the lateral surface area. Whoa, that's a stretch back into geometry, right? Right? But notice volume is area times thickness. So lateral surface area, that formula, times thickness. Well, the lateral surface area is really just the circumference times the height. That's all still the area times the thickness. So the circumference, right, because the circumference of this circle, the circumference is 2 pi. That's how I know I'm dealing with shells, right? Washers and disc only had pi. This is 2 pi times the radius of the cylinder times the height of the cylinder, all times the thickness. Remember, this is still area. Area times thickness generates volume. The radius of this cylinder, right? The radius of this cylinder is an x number. The height of the cylinder goes up to the function, right? And notice that no matter what cylinder I draw, here's another cylinder, right? There's another hollow cylinder nestled inside that one. That notice that the height of the cylinder, click and drag, the height of the cylinder, wherever I draw this strip and then make a cylinder, is the boundary is always the x-axis and the parabola. The thickness is, every time I make a slice, it's down on the x-axis. So notice, even though I'm spinning around the y-axis, I'm dealing with radii that are x values and thicknesses that are changes along the x-axis, and y is the height, but y is in terms of x. So 2 pi radius, right? The radius of each one of these cylinders is X. There's my circumference. What's the height of the cylinder? The height of the cylinder comes from the parabola, x squared plus 1, and all of this together is lateral surface area. 2 pi times the radius times the height. And each one of those cylinders has a thickness that is a small change in x. How do I sum them all up? Calculus. Notice x numbers, radius is in an x, height is in terms of x, thickness dx. Osmosis the 2 pi out of the integral, get it out of your way, and then you have x times x squared and x times 1. Power up. Divide by the power up. Second fundamental theorem. G. I get 12 pi. Notice this integrand compared to when we did this with the combination of washers and discs, right? Remember when I had to recognize that this was a cylinder, and then I was doing, right, the washer method all the way up here, right? That took a bit of doing. Since I made a vertical slice which was parallel to the axis of rotation, if I use shells, I only had this one integral. Right? That is the shell method. Now, for the AP exam will, every volume problem that they give you does not have to be done by shells. In other words, there's not one where they will say you must use the shell method. There are just going to be problems that would be nicer to do mathematically with the shell method. But if you don't want to use the shell method at all, ever, on the AP exam, you will be able to still do all the volume of revolution problems. However, for our quiz and our unit test, we are going to mandate that you demonstrate you can do the shell method by saying, use the shell method on this problem. So, I actually, had I been in class, I would have shown you, I actually have this figure, right? And when I can pull out all the shells, right? I can pull out each one of these, right? All these pieces, all these little cylindrical shells are nestled inside one another. That shape reminds me of a bundt cake, right? So this is what some of you are asking, what does a bundt cake look like? Notice that the cross sections aren't circles like a donut, right? They're kind of almost look like a rabbit. Not sure what's happening with my computer right now. Boo! Don't break down on me, computer. Ah, there we go. Oh, what is going on with my computer right now? There we go, back. Although it looks like it's in safe mode, doesn't it? So here is an applet that should be running that demonstrates these. I think this is pretty cool. There you go. You see how that's running? That's showing the cross section of the cylinders. And filling them in. See how they're hollow, they're all nestled inside one another. So those are very chunky cylinders, right? And of course, the closer the slices go together, you know, as delta x approaches 0, that's when you're going to get a really nice solid picture. So check this out. If I go here, if you hit that link, see if I can get this to... So I like these because there's animations. This is really the problem that we did, just about, right? Isn't that you see that as the warm-up shape? And you can kind of see what it looks like, right? With lots and lots and lots of cylinders. Isn't that cool again? So play around with this, you know, this applet a little bit. There's some other ones down here that I thought were awesome. Oh, there's Lane practicing across again. Look at this. I like this one. Make that curve. What does that look like when you do it with shells? Get the all the way around. Pretty cool, huh? Alright, you get the idea. So, let's try this one. Find the volume generated when this shape is revolved around the y-axis. Notice that I have a function written in terms of y, and this would be pretty ugly to say, oh, look at this figure. This figure is lying on, right, is bounded here by the x-axis. Right, so my region, why can't I do this with the washer method, right, or potato chip method? Well, because my axis of revolution is the y-axis. So if you're going to use potato chips, right, or washers, your slice has to be perpendicular to the axis of rotation. But if I'm perpendicular to the axis of rotation, notice that I would have to get this equation in terms of x, and would be, right, I'd have to get x by itself. That would be a little harrowing. So instead, I'm going to use the shell method. The shell method allows me to, even though my axis of rotation is vertical, I can make my slice vertical, parallel to the axis of rotation, which means my slices are on the x-axis, which means I can leave my function in terms of x. So a vertical slice, revolve it, and create a hollow cylinder. Here's what one of the cylinders would look like. So to set up the shell method, I need the lateral surface area, which is the circumference times the height, 2 pi RH. Get the volume by adding dx, multiplying by dx, excuse me. So 2 pi, remember you can take 2 pi, leave it inside the integral or out. X, what is that? Right, that's the radius. Here's my axis of revolution. So my radius is measured from my axis out to an x sub I, right? That distance measured from the y-axis out here to any cylinder is x, so that's the radius. What is the height no matter what slice I draw? The height is always the height of that parabola in terms of x. And I just math 9 this. These numbers, right, where do those numbers come from? The very first slice was at 2, and the last slice would be at 8. Notice that these are also x numbers. Good? You can leave your answer like this, or you can multiply by pi, but if you do, because I got 160 exactly, and then multiplied by the pi. The 160, remember, came from 2 times this integral. If you're going to use the pi and use your calculator to multiply by pi, remember you have to put at least 3 places past the decimal. Alright, what about this though? Find the volume generated when this shape is revolved around not the y-axis. Your axis of revolution has been shifted. So, what does that mean? It means you need to shift the what? The radius. Okay, so I'm going to draw. Oh, that's so bad. Continue the axes. Right? Oh gosh, I can't stand it. I could do that better. There, it's a little bit better. So I want, this time I am shifting the axis of revolution to x equals -1. So I need to take this image and I'm going to draw, reflect it across the line x equals -1. Sad. Better, but still not great, right? Oh well. Draw a strip, and I kind of, when I'm doing shells, I do actually give some dimension to my strip. And I take this strip and I draw its reflection in the image. And then I spin top. And I spin the bottom. And there's my cylinder. Oh, that's so bad. I am the worst drawer of all time. Now notice the radius has to be measured from the axis of rotation. So for this green cylinder, there's my x value. Or is it? Remember, this distance, this x sub I, is measured from the x-axis. So my radius isn't just x, is it? My radius, x is too small. Right? So the radius of my cylinder is x what? Plus this 1. So when I do my integral, since I'm doing shells, remember the strip is parallel to axis of rotation or revolution. Therefore, I'm using shells. So to use shells, I need 2 pi times r times h times d what? Your slice went down to which axis? That's right, the x-axis. So that means these numbers will be x numbers, your radius will be in terms of x, and your height will be in terms of x. What would we say our radius is? It's not just x. Because my axis of rotation has been shifted, I need to shift my radius. Out of it is the x value too big or too small? It's too small. So you need to have x plus 1. That's my radius. Notice, is my radius squared? That's for washers and potato chips, right? It's not a radius squared, it's just the radius. Now what's the height of each one of these cylinders? And then make sure you got your thickness in there. My first cylinder was drawn at 2 and my last at 8. And when you do this, you will get 192 pi. Right? I efficiented, multiplied by 2, and got 192. And then make sure I had my pi. And if you want to multiply by pi, you'll get 603.185. Good? Now look at this one. Find the volume generated when this shape is revolved around the x-axis. So revolving around the x-axis, my axis of revolution is here. The function they gave me, though, is in terms of y. That means I have to slice to the y-axis. And if you slice to the y-axis, if you don't want to slice to the y-axis, then you have to rewrite this equation with y by itself. Again, a little bit challenging to do. So, if I slice to the y-axis, the slices are parallel to axis of revolution. Which means shelves. So what am I going to do? I'm going to draw my image. Terrible. Draw the image of the slice. And then spin. And spin. Okay, so that's a cylinder laying on its side. But what is the radius? Always go to the real, like the real region. The radius is measured from the axis of revolution out to an x value, right? No, this is the y-axis. So question, is this y sub I, wherever I've drawn my slice, is that actually that length y? Is the radius y? Yes, because the axis of rotation was on one of the coordinate axes. So this is going to be my radius. Now what's the height? The height of each cylinder comes from this, shouldn't say function, I say that, right, this relation, and it's in terms of y. So how do I set this up? I'm going to do shells. It's the lateral surface area, so 2 pi r h, and then to get my thickness, multiply times d what? Because you're slicing to the y-axis, so this is dy. The radius is just y, and the height is that equation. What are my limits of integration? Since everything is in terms of y, right? These have to be in terms of y as well. What are your y values? Your first cylinder started at what? 1 and stopped at 5. So this is actually not too bad if I didn't have a calculator, even though I wrote calculator here. I don't have to do a calculator with this, right? I would just have negative 2y cubed plus 12y squared minus 10y dy. So that would be 2 pi times y to the 4th over 4, but I still have that negative 2 there, so that'd be negative a half. And then plus 4y cubed, right? Because that's y cubed over 3, minus y squared over 2, with that 10 there, and that negative 10 would give me negative 5. From 1 to 5. So negative 1/2, 5 to the 4th. Well, that's a little annoying, right? 4, 5 cubed minus 5 squared. Minus 1/2 plus 4 minus 5. And don't forget that's all times 2 pi. And 5 would go here. And right, this was all times 1, right? And when I did all that, I got 2 pi times 64. So I got 128 pi, or if I wanted to approximate that, 402.124. Alright? So there is the shell method, and we'll practice this tomorrow in class. Right? We'll have so do your homework from the book. And remember, a couple of these problems are the same problems I gave you last night, but I want you to redo them with the shell method. If you look back at the beginning, at the beginning of this, the warm-up slide, the homework tells you to do number 30 and 31, I think, again from last night, but just doing the shell method, which you should get the same answer that you did last night. So just some review here, or some wrap-up. When the strip is parallel to the axis of rotation, you use the shell method. Those shells would be dx, these shells would be dy. And the shell formula always has your constant of integration is 2 pi instead of just pi when we did washers or lifesavers. And then remember that the lateral area is 2 pi times the radius times the height, and then this is the thickness where your volume comes in. If you're doing dy, then your radius has to be in terms of y, and your, probably shouldn't be a function, right? I don't like that notation so much. The equation is in terms of y. When your representative strip is perpendicular to your axis of rotation or revolution, that's disc and washer method. Right? That's either potato chips or lifesavers to me. And notice this time you have pi. Your constant of integration is pi. And notice that your radius is squared, or your radii are squared. Good? Also, don't forget that when you shift the axis of rotation, you have to shift the radius accordingly. If you're no longer just on the x-axis, right, or the y-axis, your radius has to be shifted to represent your actual radius. Right? Maybe measuring just from the axis of from the x-axis or the y-axis means your radius is too big or your radius is too small. But a lot of times your drawing helps with that. So if you go back to the very first slide, again, you will see the homework that I mentioned. The homework, page 407 and 408, 34 to 38, all, right? 34, 35, 36, 37, 38. But then go back and look at 30 and 31. See if you can do those problems that you previously did with lifesavers or potato chips, and see if you can do the same problem with shells and get, of course, the same volume. Alright. Hope you guys have a swell day without me, and I will see you tomorrow. Don't forget your quiz is on Tuesday. See ya!